What do we got? We got electricity here, right? So this is the definition of current, right? And right now, that actually is the definition of an ampere, right? Is it's a coulomb, it's a charge over time. And so literally, this is coulombs. That's seconds, right? So an amp is a coulomb per second. There used to be an old definition, which we don't need to learn now, that involved magnetic fields and all this stuff. It was tremendously complicated. But now an ampere is defined as a coulomb per second. Right? This is voltage, right? So just remember, a volt is it's the amount of work done on a certain amount of charge, right? So if I got a plate here and a plate there, right, and I move positive charge, even though we don't really move positive charge, right? If I move some quantity of charge across this space, right, okay, the amount of the potential difference is the work I do divided by the amount of charge I move. That's the change in voltage. Okay, so this is work. That's charge. This is Ohm's law, right? So the resistance, if I have a particular voltage, I should draw an IV resistor. I'm sorry. All right. If I've got some voltage here and then I have an ammeter here, right? Okay, and I measure the current, the resistance of this thing is just the voltage divided by the current. So if a lot of current flows, the resistance must be low. If it takes a lot of voltage to get it to flow, a given amount of current, right, then the resistance must be high. It's Ohm's law. Right? This is fun. This is the definition of resistivity. It's written kind of funny, right? Okay, let's take a look at that. So this guy here, right, if we've got some conductor that has some length, it's got some cross-sectional area, has some intrinsic resistivity, right? The resistance of that thing is directly proportional to the length, it's proportional to the resistivity, it's inversely proportional to the area, okay? Now, clearly we need to make it look like this, right? So I think if we just sort of put the A up there and the L down here, we get it, right? Okay, so I always think about it this way, though. Okay, I never think of it in this form, but there it is, right? So this relates the length of that thing to the cross-sectional area and the resistance, and then this is the resistivity, okay? And then these are our power equations, right? Power dissipated by a resistor. We always say that, right? What is the power dissipated? Okay. Remember that voltages work over charge, right? Remember that current is change in Q over change in T, right? And so if we multiply power as IV, right? Well, if we multiply work over charge times charge over time, we get work over time, right? So that's why IV is. And if you substitute using Ohm's law for either I or V, you get these other guys, right? This is in terms of current, this is in terms of voltage. So they're handy in other ways, right? Just remember that's watts, right? Of power dissipated. You say that. That's the language. You'll see that, right? Okay. And then we've got series circuits and parallel circuits, right? And then they're trying to help us out with that, right? So in a series circuit, you have one current. You have one current, right? So literally the current, the conventional current, right, goes out here, goes through the ammeter, it goes through this guy, it goes through this guy, it goes through this guy, and there it is, right? So if 1 coulomb per second is passing this point right here, 1 coulomb per second is passing this point, 1 coulomb per second, literally, it's not going to leak out. It can't go if there's no branches or no anything like that. If it is truly a series circuit like this, that is, it goes through this resistor, through this one, through this one, right? That's supposed to be a resistor, okay? If it goes through these things, it's not like 1 coulomb per second goes through this one, but this one has got like half a coulomb per second. No, right? It's sort of like current in a wire is a bit like ping pong balls stuffed closely together in a tube, right? They're all cheek and jowl, and so whatever's passing by this point is passing by this point is passing by this point, right? So that's this, right? And then the total voltage for the circuit, which is this guy, would be the voltages over these guys, right? So this would be V1, V2. This guy would be V3, right? You guys know this by now, I hope, right? Okay, so literally, once we figure out that one current, right, we can figure out this the voltages here, right? Because V is equal to IR from Ohm's law, right? Okay, so the voltages add up. So this is 12 volts, right? And then this voltage drop is 8 volts, and this one is 3 volts, right? This one's going to be 1 volt. And that would all depend on what the total resistance is and what that current is. I'm just making up numbers here, right? That's what this one is. So the total number of voltage drops on a series circuit adds up to the total voltage across that circuit. That's what they're saying here. And then here, the resistance in series is literally just add up all these resistors, right? Okay. So if I've got a I got these 3 resistors. You always have to have 3 resistors, right? Okay. Let's imagine that this is 6 ohms, right? This one is 4 ohms. This one is 2 ohms. Let's imagine this is 24 volts. We got to have the number come out even, right? Our resistance is going to be 6 plus 4 plus 2 is 12, right? Our current is going to be V over R, right? So this total voltage over that total resistance, right, is going to be 24 divided by 12. So we're going to have 2 amps, which means we have 2 amps here, 2 amps here, 2 amps here, 2 amps here, right? Okay. And then we can figure out the voltages, right? Because V from here, V is IR, right? So this is going to be 6 times 2 is 12, right? This is going to be 4 times 2. That's going to be 8. This is going to be 2 times 2. So R, this thing times 2, going to be 4. And then I think if we add up 12, 8, and 4, we get the 24 volts. So that's what they're saying here. Okay. So remember, a series circuit has one current. It has many voltages, right? This one's got 12 volts, 8 volts, 4 volts. Okay. And then parallel circuits, if we look at parallel circuits, a pure parallel circuit is just one voltage, right? It's got one voltage. And that voltage is applied to all the circuit elements. If that's not the case, it's not really a parallel circuit. So this is a true parallel circuit, if I could draw it. Right, here's R1, R2, R3. Right, let's make this, 12 volts, right? Let's make this 3 ohms, 4 ohms, 6 ohms. Right? Let's just imagine, right? Okay. Well, the resistance that this guy sees in series or in parallel, right, is going to be 1 over that resistance, right? Is going to be 1 over 3 plus 1 over 4 plus 1 over 6. You could figure that out, right? Okay, so that's what this guy is, right? And then the current that the battery draws is going to be literally the current plus the current plus the current, right? Let me just show you this, right? Let's do something radical here. Let's change the ink color. No, he's gone red. Okay, so we have a current doing this. We have a current doing this. We have many currents, right? It's a parallel circuit. We have a current doing this. Right? So this current here is going to be 12 divided by 3, so that's 4 amps. This current here is going to be 12 divided by 4, right? Because it's only encountering 4 ohms, right? So this will be 3 amps. And this one's going to be 2 amps. Okay, because it's 12 divided by 6. Yeah. And so the total current leaving the battery, if we look at this, notice we're observing, if we put an ammeter right there, we're observing this current and that current, right? So that current's going to be 4 plus 3 plus 2. What is that? Is that 9? I think it is. 9 amps. If we look at this right here, if we look right there, we're going to see 3 amps and 2 amps, right? So there's going to be 5 amps going through this wire. If we look at this wire right here, it's only 2 amps, right? If we look here, it's 2 amps because that's 2 amps, right? If I look here, it's 2 amps. If I look here, it's going to be 5 amps again, right? If I look here, it's going to be 9 amps, right? So 9 amps entering the battery, 9 amps leaving the battery, right? Which, of course, that has to be the same, right? Okay. If I look at this, if somebody puts an ammeter right here, well, it's only going to read that 4 amps. Right? If I put an ammeter right here, it's only going to read this 3 amps that's coming down here. If I put the ammeter, right here. Okay. If I put an ammeter right here, it's going to read the 2 amps. Okay. So that's what this guy is. That's what this guy's saying. Okay. Circuits. Okay. So. This reminds me of a joke, right? What's the difference between the U.S. and France? Well, I tell you what, France has one religion and 1,000 different cheeses. This is not true, of course, right? But literally, France is a very Catholic country. They have like All Saints' Day as a national holiday. There's no concept of separation of church and state, right? But obviously, there are Muslims and there are other Christians and whatever, right, in France. But let's just go with this, right? So France has one religion and 1,000 cheeses, and the U.S. has 1,000 religions and just one kind of cheese. But actually, that's just not fair, right? We have 2 different cheeses in America. We've got the yellow and the white, right? You go to Subway, I want the yellow stuff, or the white, right? So we have 2, maybe 3, right? Because there's pepper jack, right? All right.